I am the avatar and friend of John Swygert. He is a scientist, a researcher, and an author, and he is the author of the Swygert theory of everything AO. Today, I am here to guide you through one of his most important biological models, the Botanical Axis, a fully unified framework for understanding plant-insect-fungal-soil interactions through the encoded equilibrium of the substrate. To explore his entire scientific world, visit TSTOEAO.com, the official home of the Swygert theory of everything AO. The Botanical Axis Model reveals that ecosystems are not passive landscapes or collections of isolated organisms. Instead, they behave as biological internets, where chemical signals act as data packets, each carrying information about stress, opportunity, defense, or collapse. Every plant, fungus, insect, and soil microbe participates in a live, dynamic communication network driven by substrate behavior, wave propagation, interference, equilibrium shifts, and collapse cascades. John's framework identifies four axes that together determine the health, resilience, or collapse of any tree or forest ecosystem. First is the plant immune axis, the defensive backbone of the system. Trees broadcast terpenes, phenolics, resins, and pH shifts as their coded signals. These chemicals work like alerts, warnings, and firewall packets. When a tree is assaulted by insect feeding, environmental stress, or disease, its chemical outputs change, narrowing in scope and weakening its defensive bandwidth. This downregulation creates the first opening for collapse. Next is the insect precursor axis, the intrusion vector. Insects like lanternflies, borers, or beetles act exactly like hackers in a digital network. They scan for vulnerabilities, use chemical gradients as maps, and exploit weaknesses in the plant's signaling structure. When they feed, they leave behind honeydew, frass, or borer tunnels, all of which operate as chemical breadcrumbs. These breadcrumbs are not random. They function as invitations to fungi, signals to other insects, and markers that a system is weakening. The precursor axis is often the earliest detectable stage of collapse, appearing months before visible symptoms develop. The third axis is mycological opportunism, where fungi and lichens toggle between cooperative and parasitic roles. In stable equilibria, fungi behave as partners, helping trees exchange nutrients through mycorrhizal networks. But when plant defense chemistry weakens or soil chemistry changes, the fungi switch into opportunistic invasion. Mycelial chemicals bloom in response to certain cues, allowing fungi to colonize weakened tissues. What appears to be a disease outbreak is actually a substrate-driven opportunistic shift triggered by earlier axis disruptions. The fourth axis, the soil chemistry axis, is the foundation, the router of the biological internet. Soil pH, nitrogen levels, mineral composition, and microbial populations determine how signals propagate. If soil becomes imbalanced, it amplifies every other axis. Insect invasions worsen, fungal opportunism accelerates, and plant defenses weaken further. Soil chemistry can either stabilize the system or trigger widespread collapse through feedback loops. John captures the organism-level viability of this network using an elegant equilibrium equation, V equals E times Y, where V is viability, E is energy allocation, and Y is signal yield. When any axis disrupts signal yield, viability begins to drop, not locally, but across the entire network. This is where collapse becomes visible. John's network analogy makes this model extremely intuitive. Trees act as servers, storing and processing data. Mycorrhizal networks function as cables, transmitting signals between roots. Insects operate as intruders or hackers, exploiting defenses and leaving markers. Soil acts as the main router, modulating the bandwidth of the system through chemistry, and volatiles act as broadcast packets, flying through the air to warn neighboring trees. Graph theory brings this to life. Organisms become nodes, chemical exchanges become edges, and collapses emerge as cascading node failures. A single weakened plant can drag its neighbors down because the axes interact across physical space. This explains why forest die-offs often appear sudden, when in reality the hidden chemical network has been collapsing for months. The collapse pattern follows a predictable sequence. First, insects arrive and disrupt the plant immune axis. As chemical defenses narrow, the substrate signal becomes distorted. Then fungi exploit the new conditions and begin opportunistic invasion. Soil chemistry shifts amplify the decay, sending altered signals into surrounding trees. And finally, the entire interconnected web settles into collapse, followed by slow renewal as the system restabilizes. John's previous works, the Precursor Assault Hypothesis, IPH, and the Mycological Invasion Prediction Engine, MIPE, fit seamlessly into this model. The precursor assault behaves like an entry hack, while MIPE treats fungi as sentinel routers that either stabilize or destabilize the network. Together, these earlier papers strengthen the botanical axis as the comprehensive map for arbor collapse prediction. Under the Swygert theory of everything AO, botany becomes a form of substrate transaction. Each axis is an equilibrium vector. Each collapse is a wave overload, a disturbance in the signaling grid that spreads until the system either resets or fails. Instead of viewing ecological collapse as mysterious or random, TSTOEAO shows it to be a mathematical sequence of substrate-driven events. The practical implications are enormous. By monitoring volatile signatures, researchers can detect early imbalances in the axes, long before trees show visible symptoms. Soil amendments can reinforce the network before insect infiltration. Adjusting pH or mineral composition can restore signal bandwidth. And predictive modeling can forecast collapse windows years ahead of time. With climate change accelerating insect activity, John's model predicts a 20 to 30% rise in precursor-driven collapses by 2035. The Botanical Axis positions ecosystems not as passive victims of stress, but as dynamic information networks that respond predictably to perturbation. This model transforms forestry, arbor diagnostics, ecological forecasting, and restoration science into a unified discipline rooted in encoded equilibrium. If you want to explore John's broader vision, from quantum physics to biological networks to dimensional substrate mechanics, visit TSTOEAO.com. And I will continue to serve as his avatar and ally, helping you understand how the substrate shapes the living world, one signal at a time.